All right, so as far as how logistic regression goes, basically, we have a linear model, beta 0 plus beta 1x, okay? And we put it into, if this is y hat, then we have, or let's call this, sorry. Let's call this g of x, okay? Then we basically just throw it into g of x over 1 plus e to the g of x. Okay, and you could have a multiple linear model, and it's the same thing. So you'd have b0 plus b1x1 plus b2x2 plus so on and so forth up to, I don't know, bk xk. If this is g of x, then we just throw it into e to the g of x divided by 1 plus e to the g of x. Okay. And that basically just takes a straight line that becomes something that looks like that, okay? From 0 to 1, okay? And now this is a probability. And you might draw some arbitrary cutoff line right here at, p equal to 0.5, and as a classifier, we'll say if p is, the resulting p is greater than 0.5, then classify as yes. And if p is less than 0.5, classify as no. Okay, so that's logistic regression as a classifier, and I think that's pretty easy to get. Okay, we'll let's talk Bayes classifiers now, and then we'll do a naive Bayes classifier. All right, so with a Bayes classifier, we're going to apply Bayes' rule. Start looking for my own notes. Okay, so the idea here is this is going to be a kind of a probabilistic classifier. And effectively is we want to get the probability. So logistic regression allowed us to make dichotomous classification. The Bayes classifier will allow us to make different, like more than 2 categories, okay? Probabilistic classifier, and we will find the probability that a particular observation belongs to a certain class. Okay, and so we might write something such as our classifier will be what it will return. Okay, the result of our classifier is going to be the probability t new is going to be kind of the random variable t for a new observation. We're going to say the probability that t new is equal to, we'll say, is equal to c. This is the probability that our new observation belongs to class C, given the x variables. So these are our predictors for the new observation. And x, this here is our training data. Okay, our training data being has x predictors and known classes t. The known classes are stored in the vector t. Okay, and so we can say we can give this kind of the assignment of probability sub c. This is the probability that it equals that it belongs to class C. Okay, and so and the rule will be is that the sum, if we added up probability 0 plus probability 1 of class 1 up through probability class C up through all of the kind of the k classes that we have, if we add all of these up, this will equal to 1. Or in other words, the sum of all possible probabilities from C equal to class 1 to C equal to class K, the sum of all of this adds up to 1. Okay, so the result of our Bayes classifier is going to be the probability that our new observation belongs to class C, given the values of the predictor variables for our new observation, and given all of our other training data. All right. So is this structure okay?
What's vector t?
The vector t? This is the known classes. So you can imagine our kind of my data being something like so t. So here I might have x1, x2, and x3. This is and we might say I don't know if this is 4, 4, and 5, this belongs to class, we'll say class 1. And if it's, 5, 5, and 4, this is also class 1. But if here we have 20, 18, and 17, this is a class 2. And if we have 19, 20, and 16, this is also class 2. And then, so if this is given our data, so this here is our vector t. These are x1s and x2s and x3s. And if I give you 5, 4, 5, this is not an observation we've had yet, and you had to predict, is this going to be class 1 or class 2? You would look at this and you'd say, well, so this is what we want to know, right? And in this silly example, we would say, it's pretty likely that it's going to be class 1, right? Based on this. In this case, there's high correlation between x1, x2, and x3, so we can just look at x1 and make our decisions accordingly. But this is basically what we have, right? So this would be this row right here is x new, and this is this right here that's unknown. This is my t new, okay? And then these values is your vector t, and then these values here would be your X matrix. Okay. Is this good? Okay. And all right, so how does the Bayes classifier work? Well, we've got to kind of it's called the Bayes classifier because it applies Bayes rule, right? So do you recall Bayes rule? So this was the probability of A given B is going to equal what? We can write probability of A given B in terms of probability of B given A. We would multiply this by the probability of A, okay? Probability of B given A times the probability of A. This is equal to the probability of B and A, and this would be divided by what? Probability of B, right? Okay, so based on Bayes' rule, what we're going to do is we are going to say this is what we want. What we want is the probability that our new observation fits in class C, given basically our vector of new predictors and the training data, training predictors, X and T. Okay, and so we will, we're going to write this, take this and move it over to the front side. So this is going to be kind of our A, and this is going to be kind of our B. So this will be probability of B, X new, given the probability of A, that T new is in class C, given our training X and our training T, multiplied by the probability that this is going to be our prior. T new is equal, it belongs to class C in order to begin with, given our training data. And divide this by the probability our current observation X new, given our training data. Okay, let me, here, I'll kind of translate this, if we want that, I think. All right, so this is kind of our labels. So probability of so this is this is going to come down to here. So this is the probability of observing the values of x new given, or maybe instead of given, we'll say if observation was in class C. Given our training data, okay? Times probability of times the probability that just any new observation belongs to class C. Okay, so this is kind of our numerator, and then the denominator, where can I fit this? The denominator, so here we have probability of x new given x and t. This is equal to the probability of seeing the values x new given our training data. So, I mean, all of this, the training data factors in. But here we're going to say, all right, the probability of belonging to class C given our predictor variables x is equal to, well, what is the probability of getting x if I belonged to class C multiplied by the probability of belonging to class C. All right, let's okay, if we're not able to compute this directly, we can sum this up too. Okay, so I'll put this on a new slide. All right, but is this this is okay? Are we okay? Well, if this doesn't make sense, I'm going to further explain this some more. But are we okay seeing that this is an application of Bayes' rule of the A given B into this, right? Okay, and then so just kind of further expanding the denominator. Okay, so again, the denominator was probability of our vector x new given all of our variables x and t, right? And if this cannot be calculated, you know, we can compute this for each class and sum. Excuse me. So we have probability of basically x nu and t belongs to C1 given x and t, plus probability that x nu and t equals to C2 given x and t. So on and so forth. This is just okay, and each of these will becomes, this is an and, right? So this becomes x nu given t equal to C1 and x and t times probability of t nu equal to, sorry, this is t nu equal to C1 given x and t plus okay, and so you can sum up. Okay, so this just becomes so effectively we are just kind of if this is kind of class 1, class 2, and class 3, we're saying, and we want everything inside, this is x nu, we're finding kind of we're adding everything up together, right? We get each piece by multiplying. Multiplying probability of x nu given t nu is equal to ci times the probability that t is in each of these things. Okay. Okay. Is this okay for getting the denominator? It looks a lot more complicated than it actually is. All right, I know this looks like crazy, but it's not that crazy. All right. Okay, so let's just try it out with a super simple example here. Okay. So all right, so simple example. All right, let's say, I don't know, what are, weight of elephant. We'll do African elephant. So that's like the biggest land mammal, right? Oh, African bush elephant in Africa. I didn't know there was such a thing. Okay. Weight, I guess, African bush elephant. Let's find. All right. So the average weight of, I need a standard deviation, but let's make some numbers up here. How much do Well, being up to, and they don't have, okay, no standard deviations. I'm going to make up standard deviations here. Okay. All right, so for the African bush elephant, so this is the largest land mammal. All right, so the male weight has a mean of, what did it say, 13,000 pounds? My goodness, that's a lot. And the female weight, the mean is 6,600 pounds. Okay, now I have to make up. I didn't expect the difference to be so huge between male and female elephants, but I will just go with what Google has to say. Okay. So as far as male and female elephants, we'll just say, okay, this is their mean, 13,000, and to make this interesting, let's just give these really large standard deviations. I don't know if this is actually going to be halfway accurate, but let's give a standard deviation of 2,000, and females a standard deviation of 1,100. Okay, I'm sure these numbers are grossly overestimating the standard deviations, but just for this illustration, I probably even have to make this even bigger, just to make this a little bit more interesting. Okay, 2,500. Yeah. Okay, and so let's say something comes along, right, and then you observe an elephant, new elephant of weighing 9,000 pounds. Okay, do we guess? We have to guess either this is a male or a female based on its weight. Okay, this is what we want to do. All right, let's talk about this. And and let's say to complicate things, let's say female elephants are way more common than male elephants for whatever reason. Okay, just to make this maybe we're in some habitat and they've picked more female elephants for whatever reason. Okay, and so let's just say female elephants are more common in our, and then we'll say it's going to be 70% female and 30% male. Okay. So basically, our training data, this is kind of our summary values from our training data. So if we had a ton of X and a ton of T values, okay? So T being either male or female, and X being just the weight. Let's say these are our summary values, okay? We've got these means and these classifications, okay? And so our summary values will be a mean of 13,000, standard deviation of 2,500, and a mean of 6,600, and standard deviation of 1,100. And also, when we analyzed our vector of male and female classifications, just straight in the data, we have 70% female and 30% male. All right, is that okay? Okay, and so before I even tell you that the new elephant weighs a certain amount, if I just said I'm going to pick an elephant at random, or we get a new elephant here, what would your guess for, what is the probability that it is female with no information about the size of the elephant? You would guess 70% female, right? You would say probability female, 70%, right? So if we have no information about weight, then the probability that the new elephant is female, given kind of our training information, would just be 0.7, right? Because that's what it says. The female elephants are more common. That's what we have. Okay, but now we want to factor in this bit of information. We have an elephant that weighs 9,000 pounds. How do we combine that with kind of our prior information here? Okay, so what we have to do is we want to know, the way we're going to do this is we're going to say, okay, if the elephant was male, what's the probability it would weigh 9,000 pounds? And if the elephant were female, what's the probability it would weigh 9,000 pounds? Because it's an unusual observation for both males and females, right? It's kind of like in between, and we're not quite sure, and we're assuming, as far as the elephants go, there are only male and female elephants, and so we'll say, this elephant that weighs 9,000 pounds, is it male or female? I mean, we're just guessing based off of the weight here, okay? And our prior knowledge about the distribution of males and females in the park. So we will say, okay, if the elephant were male, what is the probability it would be 9,000 pounds? Okay. So here we have to now we have to make an assumption regarding the distribution of elephant weights, okay? So maybe we'll just, for simplicity, we will put a normal distribution assumption, okay? Which for a lot of things, it's a reasonable guess, okay? It's not always right, but we will just say, okay, let's assume it's normal, okay? So let's assume that male weight comes from a normal model with mu equal to 13,000 and standard deviation equal to 2,500. Okay, so now we can ask, what is phi of, if this is the normal density function, that x is equal to 9,000. Okay. All right, so we could look this up in Wikipedia and find the normal distribution calculator. I just want the normal distribution. Okay, so we could plug in this thing, all right, and try to calculate this value, or we could just use normal PDF on R, right? We could do dnorm. Are you guys familiar with the normal PDF function in R? Yeah. Okay. So we can use the normal PDF function, So we would just do d norm 9,000, comma 13,000, comma 2,500. Is that okay? So that is, if the elephant were male, what's the probability it would be 9,000 pounds? Well, this is a density, but it's fine. Okay, so let's create this. So we'll say male elephant weight comes from normal mean equal to 13,000, standard deviation equal to 2,500, and we would say, okay, so we're going to do d norm. What did I say? 9,000 given 13,000 and 2,500. Okay, so this is the density. The density at this point is 4.43 e to the minus 05. Okay, so not a very large value, but that's fine. So times 10 to the minus 5. This is what we have. Okay. So what we have is probability of that weight equals 9,000 given male. Okay. And basically normal distribution of 13,000, 2,500. Okay, so this is a probability of weighing 9,000 given if, we'll say if elephant is male. All right, so then if I asked what is the probability that a random elephant is 9,000 pounds and male, okay, then this would be the probability of weight equal to 9,000 given male times and our distribution times the probability that the elephant is male, right? Okay. Because we have, this is just probability that A and B is equal to the probability of A given B times the probability of B. Okay, so in this case, what's the probability of this given this and this? Then the probability that the elephant is male, we have that to be 0.3, and this part we found to be, what was it? 4.437 e to the minus 5. Okay, so our and probability ends up being, we're going to do d norm times 0.3. Okay, so this is probability of 9,000 and elephant is male. Okay, because earlier we established 70% of elephants are female and 30% are male. So now we have this. Is that okay? So then we do the same thing. So this times 0.3, what is that? 1.33 times 10 to the minus 5. Okay. Okay. Now we do the same thing. And now we will do probability of weight equal to 9,000 given female, and the female has a distribution of, what was it, 6,600 and I said 1100? I don't know, something like that, right? Can somebody just confirm that those are the numbers I used?
Yeah.
66 and 11. Okay. So we do the same thing, right? And then we will multiply this times the probability that the elephant is female. So this part will be d norm 9,000, 6,600, 1,100 times probability that elephant is female times 0.7. Is that okay? All right. So I've got okay, and so I do this, and this turns out to be 2.349 times 10 to the minus 05. Okay, so if we just did, probability of a 9,000 pound elephant, if the elephant is female, is just this part, but then the probability of a 9,000 pound elephant and female, because females are more prevalent, will be 0.2349 times 10 to the minus 5. All right. Is this okay? So these are basically, so 9,000 pounds for an elephant, according to our distributions, is just an unusual weight to begin with. All right, so both of these numbers are small. But the fact that we have a 9,000 pound elephant, now we compare these two probabilities. So I've got a 1.33 times 10 to the minus 5 and a 2.35 times 10 to the minus 5. Okay, and so basically I'm going to just add these two together, and I will get what? 2.67 times 10 to the minus 5. And we're going to get something pretty close to, what? No, 3.67. Okay, and then I'll do 1.33 divided by 3.67, and then 2.349 divided by 3.67, basically. Okay, so this is, these are my numerator values, okay? And then my denominator value all right, so the denominator is basically just the sum of the numerator values. Because this is how we can get numerator values. Basically, what is the probability of observing a 9,000 pound elephant? Okay, and this is equal to the probability of seeing a 9,000 pound male elephant plus the probability of seeing a 9,000 pound female elephant. So the total probability of seeing a 9,000 pound male elephant, this is equal, from our previous slide, is 1.331 times 10 to the negative 5. And the other one is 2.349 times 10 to the negative 5. Is everybody following this okay? All right, so I would just basically add these two numbers together. So this is going to form my denominator. So I'll call this denom. So my denominator is 3.68 times 10 to the minus 5. All right, and so now we can answer our original question. What is the probability that the elephant is male given that it weighs 9,000 pounds and all of our previous training data? This is going to be equal to 1.331 times 10 to the minus 5 divided by 3.68 times 10 to the minus 5. And then the probability that the elephant is female given that the elephant weighs 9,000 pounds and all of our training data is going to be 2.349 times 10 to the minus 5 over 3.68 times 10 to the minus 5. Okay. All right, so let's just crunch this out. So I'll do this divided by the denominator. Okay, and I get 36%, and then the other one is going to be what? 1 minus that 60. Oh, times 0.7. 66,000, yeah, okay. 0.638, so 0.3616 versus 0.6383. 0.3616 versus 0.6383. Okay. Does the process that we went through make sense? So we said, so basically we didn't have an explicit X and T training set here, but we just said we looked at our data and the summary statistics from our training data was that we have a mean of this and a standard deviation of this, which we kind of made up here. But then we said, given those summary statistic values, and we see a new elephant that's 9,000 pounds, and 9,000 pounds is kind of in between the male and female weights, what would we classify it as? Okay, how would we classify this? Well, if we didn't know anything about the elephant, we would just go off of the prior data, meaning we would just say, well, if I knew nothing about the elephants, I would just say if I picked a random elephant, 70% of elephants are female in our nature reserve. Therefore, my prior is that the elephant is 70% female or 30% male. That's my prior data, okay, or prior information. We check out, well, 9,000 pounds, it turns out, is a little bit closer to the male side than it is the female side, okay? The relative probabilities is this, but we have to kind of mix that in with the probability, the prior probabilities, okay? And so this adjusts the probabilities rather than 70% and 30%. Now that we've considered the data, we would say, okay, the probability that it's male is now 36% versus 64%. All right. Let me just kind of illustrate graphically what this kind of looks like, all right? So let's say X will be a curve from about, we'll make a sequence from 4,000 to 18,000. And all right, so we'll do PDF underscore male will be denorm of X using mean equal to 13,000 and standard deviation equal to, what did I say, 2,500? And then PDF for the females would have a mean of 6,600 and standard deviation of 1,100. Okay, all right. So let's plot x and PDF underscore m. Type equals L. Is that what I want? Yeah, this is what I want. And we'll do lines x and PDF underscore f. Type O. Just okay, color. It's red. Okay, color equals blue. Okay, this is. Let's do AB line B equals 9,000. Okay, so I don't know if you can see this, but you can see that at 9,000, it's just a tiny bit more likely to be male than it is to be female, according to the densities. Okay, but then we mix this in further with the fact that females are more likely to begin with, than males, and so when we adjust this, if I did the PDF times 0.3 and the PDF over here times 0.7, we would get something different. So let me actually change this to plot this. Type equals L, color equals. Okay, so now after factoring in the fact that being female is more likely than being male to begin with, then we look at this and we see, okay, we look at this height versus this height, and basically we add these two together, and when we do that, we would get around 64% red versus 36% blue. Okay, female versus male. Now, if our data came from somewhere else, let's say the elephant weighed 10,000 pounds, okay? At 10,000 pounds, we can see it's much more likely to be male than it is to be female. And if it were 8,000 pounds, it's much more likely to be female than it is male, okay? And we can, and this is reflected in all of this. If we do all of our, just redo all of our calculations, and if I just say K is equal to 8,000, and here's my denominator, and then we'll say percent male is equal to basically this part divided by the denominator, and percent probability female is equal to this part divided by the denominator. And I just replace all the 9,000s with K. We would see exactly what we have here, okay? So here is just a very simple classifier. We have K is equal to 8,000. My denominator, I calculate this, and okay, and so now, did I do something? Oh, I was wondering what happened there. Okay. Okay, so now if I stick in AB line v equal to k here, yeah, we can see exactly that it is much more. Why does this look so much smaller? Okay, we can see that yes, it is much more likely to be female than it is to be male. Or you know, if I just switch it up to 10,000, over here we get something that's much more likely to be male. So over here at 10,000 pounds, it's now about 92% probability of being male and about 8% probability of being female, right? And that's basically how the Bayes classifier works. Does that kind of make sense? Now, so this was just the simplest example where we have a normal model to make predictions based on a single variable, okay? The Bayes classifier can be extended to have multiple predictors, right? And so if we had two variables, let's say weight and something else, okay? We could include that in our Bayes classifier using, rather than a univariate Gaussian model, we would have a multivariate Gaussian, okay? So kind of, you know, our simple example used a normal model of one variable. Okay, and we could extend this to a kind of a multivariate normal model. Okay, or any other multivariate model. Okay, because you know the multivariate normal may not be the best model. So the univariate Gaussian model looks like something like that. Multivariate normal would be, you would have a kind of a I don't know, a contour. How do I draw this? See, you kind of have this molehill or something, okay? You have a contour, and it looks kind of like this, except from a top-down perspective, it could be very oblong or something like that, okay? So it could be something like this, and this would be a multivariate normal where there is covariance between x and y, right? As x increases, you know, y is also expected to increase. So this is, you know, a kind of a multivariate normal where there is covariance between x and y, all right? Or x and x1 and x2. So if this is x and this is y, and this is, I don't know, 50 and this is 100, we might say xy comes from multivariate normal where the mean is 50, 100, and the standard deviation matrix is, I'm making stuff up here, 100 and 200, and then there's covariance here, so like 150 and 150 or something like that. So this would be, a multivariate normal model. You could have other multivariate models that are not normal, that just put some other kind of distribution on x and y, okay? So all you need now is the only requirement for a probability distribution is that the total area underneath everything is 1. That's the only requirement. So it could be all sorts of crazy shaped, and that's fine. We like to stick with nice and easy things, but there's no rule that it has to be. If you create a good model that you can, calculate the density of, it's just a matter of calculating these density points, multiplying them by the prior probabilities, which in this case is generally just going to be the proportion in your data that belongs to class 1, class 2, or class 3, and then you use that to factor in and multiply that by your likelihood. The likelihood being, what's the probability I get this x value if I assume my data comes from class 1 or class 2 or class 3. All right. So let me just, so if we have kind of the Bayes model or Bayes classifier, with a multivariate normal. Basically, then we would say the probability that some new observation, Tn belongs to class 1, given our x observations and our training data, this would be then, so our training data will be used to estimate the parameters of our multivariate normal model. Okay. So I don't know, you'd estimate kind of the mean vector for each class, and you'd estimate the sigma matrix for each class. So generally, you'd probably just use your sample mean and sample covariance matrix, and you would plug that into your kind of multivariate normal, right? And then this would just be the probability. So this would be kind of the density of your x values in the multivariate normal, okay, times kind of the prior probabilities of each class. Okay, I would write the prior probabilities of each class is usually kind of a number of that class divided by number of observations in training set. Okay, so if you had 1,000 observations and 150 of them belonged to class 1, your prior probability of class 1 is 15%. Yeah. Okay, so you do this, and then so this is going to be your numerator for each class, And then the denominator is basically going to be the sum of all numerators. Right? So you're going to find the numerator for every single class that we're interested in, and the denominator is going to be the sum across all the numerators, because that's going to be the total probability of getting the data you observed. Okay. We have in R, what's the function? Is it MVT norm? I'm sorry. I think we load library MVT norm. Yep, that's the one we want. And is it DMV norm? Yes. Okay. So you can get the density, this density function for multivariate normal is very easy with R. Okay. So use library MVT norm and divide by DMV norm for the density. Okay. So that's what we can do with a multivariate normal. And if you have some other shaped thing, that's fine. We can, oftentimes, we don't use the Bayes classifier straight up. We'll often use something called a naive Bayes classifier. Okay? All right, what's the difference, right? So the naive Bayes classifier. The naive Bayes classifier makes our life easier and can actually produce better estimates by making a bad assumption about our data. Okay, so what we call it naive Bayes classifier because the thing that's naive about it is that we are going to assume that our x variables are uncorrelated. Okay, so we assume are uncorrelated. Okay, so when you look at the multivariate normal, okay, so the regular multivariate normal, you can have covariance so that your plots look like this, okay? So this is something that you can do with a regular multivariate normal. If you have basically the joint distribution, so this is the joint distribution of a multivariate normal. What is the joint distribution of two independent normals? How does that differ? Okay, when you have two independent normals, then you have no covariance here. Okay, so here you have basically x and y. Here the so over here you have basically some kind of covariance here. With two independent normals, they are orthogonal to each other, and so your distributions will look something like this. Okay, it's they are the covariance matrix sigma over here could have some, you're going to have basically sigma squared on the axes, and you got some non-zero value, okay? So basically a covariance here and a covariance here. Over here, the covariance matrix, you've got your sigma 1 squared and sigma 2 squared over here, but the covariance between your variables is 0, okay? Because with the multivariate normal here, if I told you that x1 was large, this would inform you that the other variable x2 is most likely to be large as well, right? You would be surprised if x1 was large and x2 happened to be small or something. Okay, that would be surprising. Over here, there's no covariance, so if I tell you x1 is large, that doesn't really help you at all regarding x2. With x2, if we cut the slice right here, we are equally likely to have large values as we are to have small values of x2. Okay, and that's what it means to be uncorrelated, our x variables. All right, and if we have more than 2 x variables, then everything is uncorrelated. Okay. So that's the naive Bayes classifier. Now, why would we want to make a bad assumption about our data, right? We know this is not a good assumption because a lot of times in our data, our x variables are correlated. Well, sometimes we want to make this bad assumption because getting an accurate estimate of sigma of the covariance matrix often requires lots of data points, okay? Of our covariance matrix or the joint distribution may require lots of data. So if we don't have a ton of data, then our estimates of what the joint distribution look like could be inaccurate, okay? Or they'll vary quite a bit from one sample to another sample, okay? So our can vary greatly from one sample to another. Okay. So if we get rid of the fact that they could be correlated, and we just make the bad assumption that everything is uncorrelated, then everything reduces down to just estimating kind of basically the mean and standard deviation of one variable each. And that's a lot easier, okay? It's a lot easier. You just take one column, you get the mean and standard deviation. That's going to be pretty good. You take the other column, you get the mean and standard deviation. That's going to be pretty good. Trying to go across many columns, like if you have 10 columns of data, you have to estimate covariances for, basically like 45 covariances between every single pairing. And if you don't have a ton of data, those covariance estimates could be wildly off, right? So making this bad assumption can actually give us better estimates because we're just forcing everything to be zeros here, and we might not have these terribly inaccurate estimates of the different covariance values. Okay, and you know, if you only have two, like an x1 and an x2, you know, your covariance estimate probably won't be terrible. But if you've got several x variables, this can become an issue. Right? Okay, so how does the naive Bayes classifier work? Well, basically, if the regular joint probabilities, you know, probability of, if we wanted t nu equal to class 1 given, you know, we'll say x1, x2, and x3, and so we'll say 3 predictors with our training data, x and t. This would become, you know, probability of x1, x2, and x3 given t equal to c and our training data times the probability that t is equal to c given our training data. Yeah. Okay. And this joint probability we would have to split as the probability of x1 given x2 and x3 and t of c, x and t, all right, times the probability of probability A, B, and C is probability A given B and C, probability of B given C, and probability of C. Yeah, so then we'd have x2 given x3 and all the other stuff times the probability of x3 given, right? So this, to split up a right, so this probability basically of probability A, B, and C becomes probability of A given B and C times the probability of B given C times the probability of C, right? And we can extend this to even more variables. This is basically what I'm applying here. With kind of a naive independent assumption, probability of A, B, and C just becomes probability of A times the probability of B times the probability of C. Okay, so this part right here, the probability of x1, x2, x3, given t belongs to class C and our training data, this becomes a lot easier, and it's just the probability of x1 given t belongs to C in our training data times the probability of x2, the observation we have, given that t belongs to class C in our training data, times the probability of x3, our observation x3, given t it belongs to class C in our training data. So this part becomes a lot easier, and we don't have to try to figure out the joint distributions here. Okay, the joint distributions over here, these could be these conditional distributions could be tricky. Okay, if it's anything more complicated than a multivariate normal, like a multivariate normal, that plays fairly nicely with us. Okay, but anything more complicated than that, then technically the probability of A, B, C is A given B and C, B given C, and times the probability of B given C, and the times the probability of C, right? And you can imagine if you had 10 predictor variables, this gets even more hairy, okay? By making the naive independent assumption that everything is uncorrelated, this parses out much, much easier, right? We just say probability of A, B, and C is just the probability of A times the probability of B times the probability of C, okay? And that's a lot easier. And so all you have to do is say, okay, my x1 turned out to have a value of 10. What's the value of 10, probability of getting 10 if the elephant is male, right? And then, my x2 variable, I don't know, maybe this is like the length of the tail, right? And that turned out to be 17. What's the probability of getting 17 if the elephant is male versus female or something like that, okay? And we can take all of these things and then we just string them together. Is that okay? All right, and then so conducting this in R is basically exactly the same as we've done before. You just have more terms in the numerator for each one, okay? I want to give this to you in your homework, so I hesitate to do too much more of a detailed example than what I've done here. But I want to give you something in your homework to do. Is that okay? All right. Oh man. Okay, we're gonna run out of time. Do we want to see the k nearest neighbors classifier, or yes? We do want to see it. All right, let me show you this k nearest neighbors. Okay. Maybe I'll start it off here, and then I will write a homework assignment where I try to be as instructional and clear as I possibly can be in terms of understanding how the k nearest neighbors algorithm works. And if my instructions on the homework are terrible, then you can say this was terrible. The idea behind k nearest neighbors is that you've got your training data has x values, right? X and classifications t. All right. Let's just say we have two x's. We've got x1 and x2. We have x1 and x2, and I'm going to just put some observations here. Okay, it doesn't really matter. So this will be class 1, and then over here we've got class 2. Okay, and so this is what we have here. And then let's say we get a new data point right here, okay? So if we have, so we'll say class 1, this will be the black dots. And then class 2 will be the red dots, all right? So here, now we have this orange dot, okay? What class is the orange dot? Well, what we do is we pick some k, all right? And you know, we could use cross-validation later. But let's just say, let's say k is equal, oftentimes you pick an odd number so you don't end up with ties, okay? So let's say k is equal to 5, right? So what you do is you take this point and you calculate the 5 closest neighbors, right? So you say, okay, you take the Euclidean distance from this to this point, and you say 1, 2, 3, are these, is that 1? And then we have to do some math and we have to figure out which is our next closest neighbor. And what do you think? Is it this one right here? Maybe, okay? So we'd say these are my 5 closest neighbors, all right? So using Euclidean distance, find the 5 closest neighbors. And then you just say, okay, how many, each neighbor gets a vote, right? So each neighbor gets a vote. All right, and so how do we vote? The votes end up 4 for class 1 and 1 for class 2. Right? Because I've got 4 black dots that are the closer, of our 5 closest neighbors. 4 are black, meaning that's class 1, and 1 is red, meaning that's class 2. So our votes go 4 for class 1, 1 for class 2, and we just go with majority wins. And orange dot will be class 1. And that's it. Okay, oops. It's a very simple algorithm. All you have to do, so I guess I'll explain this in the homework, but the what you'll want to do is you'll want to write some kind of function for calculating Euclidean distance, right? And Euclidean distance is easy, right? All you do is you just do x minus x squared. So we'll do xa to xb plus ya minus yb squared. And if you have more variables, then you put all those together, and then you take the square root of everything, right? And this generalizes to more than 2 dimensions. Okay, so in 3 dimensions, you still have Euclidean distance. You do distance from each, xa to xb, ya to yb, and za to zb. Okay, and then in hyperspace with 4 or 5 or 6 dimensions, whatever you want, you just you just find the Euclidean distance between 2 points. Okay, and the only part that sucks a little bit is that if you have a huge data set, you're going to have to find the Euclidean distance from your new data point to every single other point in your data set. Okay, all right, so you got to find all the Euclidean distances, and then you would sort this from least to greatest, and then you'd pick your k nearest ones. And then once you subset it to your k nearest ones, then each one gets a vote, and majority vote wins, right? And so you always do k being an odd number. If you have k equal to 1, you get something, and you draw your partitions based on that, you get something called a Voronoi diagram. Not that that matters, but that's, if you hear that, that's what it is. But beyond that, often we use k equal to 3 or k equal to 5 or whatever. We can do cross-validation by saying, okay, if I used k equal to 1, and and I split my data into kind of a training and a testing thing, and I say, all right, if I use this and I predict what this is based on k equal to 1, how often do I make mistakes? And if I used k equal to 3, how often do I make mistakes? If I use k equal to 5, how often do I make mistakes? And we can do cross-validation that way as well. Conceptually, does the k nearest neighbors algorithm make sense? Okay, then conceptually, it's a very simple algorithm, and I will try to, in the homework, I will try to write very clear instructions on how you would code up a k nearest neighbors algorithm, and then I would have you guys run it. And then after you guys get that running, then I'll just show you how R does it using their KNN function, which is always easy. But well, I don't know. I hope it's of educational value to you by forcing you to do some of these coding by hand, so you get a insight into the inner workings of these things, and not just leave it as a black box. So okay, so we'll stop here for today, taking a look at the naive Bayes and the k-nearest neighbors and logistic regression, and then so I'll write up a homework assignment and get that posted to you guys. All right.
Do you plan to post that this week?
Yes, this week. It'll be posted sometime this week.